Hey guys, you're back here for AP Chemistry with Miss Gray. Today we're going to have a lesson in physics. So, I know it says periodic table, but really it's a physics lesson. This is podcast 6.5, and we're going to talk about the trends on the periodic table and how elements respond to other elements. So, if we look at the periodic table itself, it was developed by two different scientists, Julius Lothar Meyer and Dmitri Mendeleev. Both were working on this, but Mendeleev was the one who published his first, so he gets credit, right? Neither of them really knew much about atoms. They knew that atoms existed, but they didn't know much about what they were made of. So what they did was to put the elements in columns according to their similar chemical reactivities. And Mendeleev called this combining capacity, like how elements combined with others. And because he was so careful in his measurements and in grouping them together, he also was able to predict the properties of any missing elements that hadn't yet been discovered. When they were discovered, his predictions were correct. And so that's why he's credited with having put together the first periodic table, because his was the useful one. So what is it that keeps our electrons in an atom in the first place? Since it's the electrons that determine reactivity, what is it that holds them there? So here's where physics comes in. The electrostatic force keeps electrons around an atom, and it's described by what's called Coulomb's law. So the force of the attraction for a positive particle and a negative particle is described by Coulomb's law, where K is just some constant, right? Because constant always starts with K. Yeah? Okay, maybe not, but K stands for constant. And then Q simply represents the charge of the particle that we're talking about. And so in this case, a proton is a +1 and an electron is a -1. And so that makes for easy math, right? Because we take 1 times 1, and that's always equal to 1. Woohoo! And then R is the radius, or the distance between our two charges. So that's Coulomb's law, but we're going to come back to this over and over because this dictates the interactions between our positively charged nucleus and our negatively charged electrons. So here's basically what we mean with Coulomb's law. The higher the nuclear charge, the higher the electrical force is. All right? So, in other words, if I double the charge, what's going to happen to the force? The force doubles, right? And so now what would happen if I quadruple the charge? Then that would have the effect of quadrupling the force as well. So when the charge increases, the force also increases, right? And for nuclear charge, if you want to know how to find this, it's the atomic number on the periodic table. So hydrogen has a nuclear charge equal to 1 because it has 1 proton. Lithium has a nuclear charge equal to 3 because it has 3 protons. It's that easy. Oxygen is number 8, and so it has a nuclear charge of 8 because it has 8 protons, 8 positive charges. So that's how we determine the nuclear charge. And the higher the charge, the greater that electrostatic force that holds the electrons around the atom. So that's going to be super important. Now let's look at another factor to consider. The greater the distance between the charges, the weaker the attractive force. Look, it's an inverse proportionality, right? So as the denominator increases, that means the force is going to decrease. But this isn't a simple inverse proportion. This is known as the law of inverse squares. And so our force is going to weaken dramatically as the radius between charges increases. Let me show you what I mean by this. Suppose that we double the radius. Then what would happen to the force? It's going to decrease, but it doesn't decrease by 1/2. It decreases by 1/4 because we square the radius. See, it's the law of inverse squares. So as the radius doubles, the force is cut by 1/4. It's 25% of what it was before. Now let's take that electron even farther away from the nucleus. Let's quadruple the radius now. What do you think will happen? Quadruple squared means we get 1/16 the force. And so we have a dramatic decrease as the distance between our charges decreases. See how that works? So which factor seems to have more of an influence on the force between particles? Is it the nuclear charge, or is it the distance from the nucleus? That's right, it's the distance from the nucleus. That has a much larger impact on the electrostatic force. So let's look at how to measure the effective nuclear charge. We have this equation that's called the Rydberg equation. I'm going to write that down for you. And I think we've already looked at the Rydberg equation in another podcast, right? Yes, we did? Yes, of course we did. So we take our constant multiplied by the effective nuclear charge divided by the energy level where that electron is, the electron that we're interested in. So usually we're more interested in the change in energy, and so that would be the change in energy levels as we move from one shell to the other. So if you didn't know how to calculate this, go back to the previous podcast where we talked about the Bohr model and see what do we do with the Rydberg equation. Was that the third podcast, I believe? So this is where the effective nuclear charge calculations can come from the energy that we're measuring. So we can use this Coulomb's law to predict properties of elements. So we use the effective nuclear charge to predict how it's going to react with other things. And the amount of energy it takes to remove the electron is called ionization energy. Ionization energy is governed by Coulomb's law. Okay, so let's look more closely at the Rydberg equation. Here's what I want you to see. Since we said this was true for the Bohr atom, then we want to know when it applies and when it doesn't. But the Rydberg equation can also be derived from the quantum mechanical model. And so we can use this amount of energy to predict for any atom and any electron and any energy level approximately how much energy it will take to remove that electron. So usually we're dealing in moles, right? And the amount of stuff with moles. Not just one electron at a time, but a mole of electrons. And so then, taking the Rydberg equation, we would say, for one electron, it's this much energy. Multiply that by the number of electrons per mole, and you get for a mole of electrons how much energy. So do this math, multiply these two numbers together, and you should get 1.13 times 10 to the 6th joules per mole. So let's convert that to something more familiar to us. Remember from thermochemistry, we talked a lot about the number of kilojoules per mole. To remove a mole of electrons from their nuclei, it would take 1,310 kilojoules per mole times whatever the nuclear charge is squared divided by the energy level squared where that electron is. That's how we solve these. So we can work for any kind of atom in any energy level that we want to. So this gives us an ionization energy that we can actually use to describe what the properties are going to be like the electronegativity for an element, for instance. Ionization energy for a 1s electron from sodium, using this math, is 1.39 times 10 to the 5th. And that comes from sodium having the nuclear charge of 11 protons. All right, so we put 11 in for Z. And then it's the 1s electron, so we put for n equals 1 here. All right, that's all we did. And when we do that math, this is the number we get. Let's compare the ionization energy for that 1s electron, the innermost electron, to an electron that's in the 3s energy level. For sodium, if you're in the 3s, then you're the valence electron. Look at how much less energy it takes to remove a valence electron from sodium than it does to remove that core electron from sodium. So this would be 495 in decimal notation, and this would be 13,900, right? 2, 3, 4, no. 139,000 kilojoules per mole. So this is much, much higher to remove a core electron than to remove a valence electron. And this is what provides evidence for shielding. The phenomena of shielding is really critical here. So we want to make sure that we understand how nuclear charge works, but we also need to understand how shielding works. Let's spend some time on that. So shielding is where we take electrons on higher energy levels that tend to be farther out from the nucleus. So that Coulomb's law, remember we had the charge of the particles divided by the square of the radius. To be farther out means a weaker electrical force. So keep that in mind. We have a weaker electrical force because you're farther away in the first place. But here's another complicating factor. These electrons on the valence shell have to look through other electrons to see the nucleus at all. And so they're less affected by the nucleus anyway. So let's draw lithium's Bohr structure. So lithium has 3 protons and 4 neutrons. And since it is in the second row, we know we have 2 rings of electrons, 2 electrons in the first ring, and only 1 electron, that valence electron, sitting in the second ring. So to see the nucleus, this valence electron has to look through 2 other electrons to feel the force of that 3+ nucleus. Now let's compare that to sodium, say. Sodium has 11 protons and usually 12 neutrons in the most common isotope. And it's in the third row. So we have 2 in the first ring, 8 in the second ring, and then 1 electron in the outermost ring. So here's our valence electron. So normally we would predict that something with 11 protons can pull harder than something with 3. But we've got all these electrons in the way blocking us, plus we have a greater distance from the nucleus. So the radius here is much higher. So our Coulomb's force, the electrostatic force, is smaller, and this 10 core electrons are shielding the valence electron from the nucleus. Now let's compare that to francium. I need a periodic table so I can look at francium, because I didn't memorize how many that one has, how many protons. Okay, here's my periodic table. 87 protons. Are you kidding me? All right, back to where we were. Okay, let's draw francium's Bohr structure. We have to find a home for 87 electrons, however many neutrons, but we need 7 rings to put all the electrons in. 2 go in the first, 8 in the second, 18, then we get 32, 18, 9, and 1. 9, 18, oh dang, I don't know. That doesn't add up to 87. Let's see, 2, 8, 18. Then we go up to 32. This one's going to have to be 32. Then fill this 6 fills up with D, S, and P. So 18. Okay. 32, 32, 18, and 1. All right, now we got it. Hopefully that adds up to 87. But you get the point, right? Here's our valence electron that's being tugged on by 87 protons. But look how far away it's going to be from the nucleus. That radius is way bigger than it was in lithium. And all these electrons, there's 86 electrons that are blocking my valence electron from seeing the nucleus. This is what shielding is all about. Since this electron's being blocked by all those other core electrons, then it's shielded from the nuclear charge. It's less affected by the nuclear charge, and it's held more loosely. So francium gets rid of this electron much more quickly than lithium would get rid of its valence electron. And so its ionization energy is very, very low. It's the lowest on the whole periodic table. Ionization energy is very, very low. that means its reactivity is very high because it gives away the electron at the first opportunity. Another thing to consider too is that since it holds this electron with less energy, then it can't pull it in as close because it can't hold on so tight. And so the atomic radius is going to be huge for francium. Atomic radius referring to the size of the atom. So the atomic size is much larger for francium compared to the other alkali metals because it just can't hold on to all those electrons, in particular this valence electron that's being shielded. So what shielding does, essentially, is to reduce the overall effective nuclear charge. Of course, that's not all there is to the story. There's more to it than that. Penetration is the idea that some electrons are going to be closer to the nucleus than others. So there's levels to the electron distribution for each type of orbital. Let's look at a graph of this. So what I want you to see is the peaks on the graph that show where's the most likely location for an electron around the nucleus. So this peak would give us the most likely place for our electron to be. And this is the graph for the 2s electron. I know that's hard to read because it's white on yellow, so that's why I'm pointing it out. This is the 2s electron. Now let's look at an electron in the 3s. Okay, so now our peak, our first peak, moves in closer. Remember, these peaks come from nodes and antinodes. The peak represents an antinode. The valley represents a node where the electron is not allowed to be. So the peak is our most likely place for our electron. In the s orbitals, it's pretty close to the nucleus. Our first antinode is really close to the nucleus. Here's where our peak would be for a p orbital. And then for a d orbital, it's way back here. So penetration refers to how close the electrons can get to the nucleus. It's much closer in the s and in the p than it is for the d. Now let's look at the 4s. Here's our 4s. Look how close that can be. This is why electrons fill the 4s before they fill the 3d orbital. Electrons will fill into the lowest energy level first, and it's lower energy for them to be in 4s than it is for them to be in 3d. Since transition metals, though, can put electrons into an energy level lower than their valence shells, it's kind of like a metal can tuck an electron down into its pocket so it doesn't have to share it with anybody else. It can keep it to itself and only share the electrons in the 4s shell. Pretty nifty, huh? Penetration effect has a major impact on how the orbitals fill. So the outer energy levels penetrate the inner levels. The 4s penetrated the 3d, so that the shielding of the core electrons is not totally effective, and that affects the properties of the elements we're looking at. But most let me start over. From the most to the least penetration, we go in order of S, P, D, F within the same energy level. So what this means is that electrons prefer to fill in the S and the P energy levels before they go into the D and the F. But when they do go into the D and F, their energy level drops down to something lower, so they won't be valence electrons anymore. So we fill in the 4s before the 3d because in the 4s, the penetration is higher than it would be for a 3d orbital. So this is the phenomenon that gives us the order of filling the electrons, where they're more stable in s and p orbitals. All right, so what we know is that the more positively charged the nucleus is, the smaller the orbital will be, right? This is all about effective nuclear charge. Think atomic number here. So the sodium has a 1s orbital, and hydrogen has a 1s orbital. They're the same shape, but in sodium, it's going to be smaller than it is in hydrogen because sodium has 11 protons to pull on that electron with, and hydrogen has only 1. Now we're not saying that the entire atom is smaller, just the 1s orbital is smaller. When we're looking at the atom as a whole, the atomic radius for sodium is bigger than that for hydrogen because we got to fit more particles in. So we're just talking about comparing the size of the 1s orbital. It's going to be smaller for sodium because the effective nuclear charge of sodium is higher than that of hydrogen. So let's talk about periodic trends then. That's what we're leading up to. The ionization energy is the energy required to remove an electron from a gaseous atom. An atom in its gaseous state, we want to take its electron away. That's called ionization energy. So the first ionization energy, I1, is the energy required to remove the highest energy electron, the valence electron, the one that's farthest out from the nucleus, all right, where N is the highest. And then second ionization energy would be the second highest electron, and so on. So we'd have a third ionization energy and a fourth, and so on. So let's have a real example of an actual element we might be working with. Hey, sorry for the interruption. You know, the bell rang. Kids wanted me to teach them, so I did. So we're back anyway to the podcast about periodic table and physics. We were looking at trends in ionization energy, and now we're going to have a look very closely at magnesium. Remember, magnesium is an alkaline earth metal, so it normally has 2 valence electrons, right? And since it's a metal, it tends to donate electrons. To get to an octet, the easiest thing to do is to give away these 2 electrons and form the magnesium 2+ ion. So what you'll see over here is that the energy to remove the first electron, I1, is 735 kilojoules per mole, which is much lower than removing the second electron, 1,445 kilojoules per mole. That's because after the first electron is gone, then we have 12 protons that are pulling on now only 11 electrons, right? So it can pull them in tighter, the radius decreases, and so it's going to have more electrical force. But now look what happens when we try to get a third electron away from magnesium. See, once the first 2 are removed, then all we have left are core electrons. Look at the incredible jump in ionization energy when we go from taking away valence electrons to now taking away core electrons. That's an awfully lot that's a really big amount of energy that's not very likely to happen. Not under normal conditions anyway. So what we see is that the effective nuclear charge increases as you remove electrons because the radius of the atom can get smaller. It takes a lot more energy to remove a core electron than it does to remove a valence electron because with a core electron there's less shielding. So let me draw that Bohr model so you can see what this looks like. For magnesium we have 2 in the first ring and 8 in the second ring and 2 in the third. That's what magnesium would look like. And if we take these first 2 away, then now we're into the second ring, right? So now there's only 2 electrons shielding the valence electrons, and they experience much more of this 12 positive nuclear charge than these electrons did out here in the valence shell. All right, so now it's your turn. I'd like you to look at another set of data and see if you can come up with an explanation for why aluminum has these ionization energies. There's 4 of them. So the first one represents removing the first electron, the second would get a second electron away, the third removes the third electron, and the I4 would take the 4th electron away from aluminum. So write in your packet your explanation for why we see this trend in ionization energy. It's okay. You can hit pause because I'm moving on. So as we go across a period, remember periods are side-to-side rows, then as we go from left to right, the ionization energy is going to increase because, although shielding is constant, there's a greater amount of positive charge. So there's a larger nuclear charge as we go from left to right. So generally speaking, ionization energy will increase as you go from left to right. And I say generally because, there's going to be exceptions to the rule. But basically, nuclear charge and shielding determine all there is that we need to know about periodic trends. And if they're in the same row, then it's about nuclear charge, not about shielding, because shielding would be the same. Now, as we go down a group from top to bottom, then the ionization energy decreases because electrons are farther away from the nucleus. In other words, the effects of shielding are greater the farther down the group you go. And of course, it's not that simple. We know that the effective nuclear charge changes as you go across the period, and so does the ionization energy. But there's also the whole idea of shielding and penetration and all that nonsense. Here's one thing to consider. If you have a halfway filled orbital or a completely filled orbital, then it's much more difficult to remove an electron. So let's look at the 3D orbital, for instance. We already talked about why the chromium family and the copper family would be considered exceptions. So if we had this type of configuration with 5 electrons in the 3D orbital, then this is what's considered a half-filled orbital. Since this is so stable, then we would see a spike in the ionization energy when we get to this particular configuration because it's more stable than having, say, 4 electrons here. So chromium kicks an electron out of the 4s and moves it to the 3d so it can achieve this more stable configuration of 5 electrons, a half-filled orbital. And of course, if we completely filled it in like zinc does, then we would have even more stability, right? So then it would be harder to remove an electron from zinc than from, say, gallium, which even though it has a larger nuclear charge, it has less stability because its 4p would only have 1 electron in it for gallium. So if we were to graph this, this is what the trend would look like. So you see all of these in the 3D are relatively stable. We have some spikes where we have more stability than others, but basically what you see is the metals tend to have very, very similar properties because their valence electrons are in the 4th energy level, not the 3rd. The atomic radius represents like the size of the atom, right? So if the nuclear charge is larger, it can pull tighter on the electrons, and that would make the atomic radius smaller because the nucleus pulls the outer electrons in closer. And if effects of shielding are greater, then it can't hold on to its electrons quite as well, so the radius would be larger when the effects of shielding are greater. So now let's look at these 2 atoms. Let's explain why the radius of lithium is larger than that of beryllium. So lithium has 3 protons in its inner ring and 4 neutrons. 3 protons in the nucleus and 4 neutrons. 2 electrons in the first ring and only 1 electron in the outside ring. So we're concerned about where's this valence electron going to be. Let's compare that to beryllium. Beryllium has 4 protons and 4 neutrons, maybe 5, I don't remember. Not important because the protons are the ones that we care about. And then 2 and 2. So we're looking again at the valence electrons, not the core electrons, and where are they going to be in relation to that nucleus, the positively charged nucleus. So since the effects of shielding are constant, they both have only 2 electrons blocking the nuclear charge, then it's not about shielding, it's about the effective nuclear charge. And for lithium, its effective nuclear charge will be less than the effective nuclear charge for beryllium. Why is that? Well, look at the number. 3 is less than 4. And because of Coulomb's law, we know that a greater charge means a greater force, right? There's the rest of our Coulomb's law. All right. So the next one asks us to explain why the atomic radius of titanium is smaller than that of zirconium. And gosh, I'm going to need a periodic table. And I don't have it. Oh, look, got my phone. Of course I have a periodic table. I always do. Titanium is number 22. And then zirconium is number 40, which is located directly below titanium. So on the periodic table in the D block, you'll find titanium here and zirconium right beneath it. So we're going down the row. Shielding is not constant here. The effects of shielding are greater for zirconium than for titanium. Thus, the atomic radius will be larger here because zirconium cannot hold on to the electrons in its valence shell nearly as well as titanium. So it's always about nuclear charge and shielding. Let's look for patterns. When you're looking at the periodic table, there's certain groups that I need you to know. And it's based on how they react and what they do when they interact with other types of elements. So we're looking at the number of valence electrons because that's what determines the chemical properties of an atom. Valence electrons are on the outside ring, so naturally they're the ones that are going to come in contact first, right? The ones on the outside. So what we know is that metals donate electrons, and since they do, they have the lowest ionization energies. Nonmetals like to accept electrons, and so they have the most negative electron affinities. Affinities is like affection. They like electrons. And because they're the most negative electron affinities, that means they like them the most. So let's look at alkali metals. Group 1 is the alkali metals. They have only one valence electron, kind of like hydrogen. But hydrogen's not included as an alkali metal because it's not a metal, it's a gas, right? It behaves as a non-metal. So here's what we know. From top to bottom, we could list these. We have lithium, sodium, potassium, rubidium, cesium, and francium. From top to bottom, we're going to have more shielding, right? So we have a decrease in ionization energy, an increase in the radius, decreasing density, a decrease in melting point since they don't hold together nearly as well, and they behave as reducing agents. Remember, Leo says Gur? Loss of electrons is oxidation, and since these guys get oxidized, they will cause a reduction in something else. That's why they're dangerous for you to try and purchase and store for a laboratory or for any other purpose. Lower ionization energy means it has a better reducing ability. It's more able to donate electrons where it has a lower ionization energy. So here's the order of reducing ability from greatest to least. So francium gives the electron away the easiest, and lithium holds on to it the most. But compared to other elements, it doesn't hold on to it very tightly, does it? This works pretty well for solid elements, but it doesn't work for elements in aqueous solutions. Once we put these elements in water, then we see a difference because of the energy of hydration. And we'll talk about that once we get to talk about intermolecular forces and colligative properties. In other words, properties of solutions. All right, let's look at alkaline earth metals. Group 2. These guys all have 2 electrons in the valence shell. And so they're very reactive, and just like alkali metals, they're rarely found in their pure form, especially out in nature, because they react with air, they react with water, and so once we find them, they've already interacted with those other elements and compounds, and they're now in the mineral form, not in their pure elemental form. Okay, noble gases are next. These guys are always found in pure elemental form because they have a full valence electron shell, so they don't react with anybody. Xenon, of course, has been forced to react under extreme conditions to make xenon tetrafluoride. But we had to use fluorine, which is the most reactive element, so that we could get xenon to react, and it was under incredibly severe conditions of extreme pressure and very, very low temperature. So they don't normally form compounds. They just live as elements all on their own. Halogens, though, are very reactive. The halogens are in group 17. All they lack is a single electron. They have 7 in their valence shell. If they had one more, they would be like a noble gas. So here's fluorine. Fluorine has a very tiny atomic radius because it has this nuclear charge of 9 protons and only 2 electrons shielding the inner ring, with these 7 electrons floating about the outside. So if we had one more, fluorine would be like a noble gas, and it would be much more stable. So it does everything it can to steal that electron from somewhere else. Halogen means salt former, and these elements were called halogens because they're found in salts. The compounds that they form when they react with metals are called salts. Right? Let's look at transition metals. These are the ones in the D block, groups 3 through 12 in periods 4 through 7. But it also includes the rare earth elements. So sometimes they're all lumped together because they behave a lot the same. Other scientists like to keep the rare earths separate because they fill electrons into f orbitals. But the thing to remember is that the D and F electrons are not valence electrons. They're going into lower energy levels, so they get to be core electrons, and the electrons that get donated are coming from the s orbitals most of the time. Transition metals tend to be very hard. They have a high melting point, and they're often used to mix together in the form of alloys like brass and stainless steel or pewter and bronze, because then we can get the most desirable properties of both elements and make something even better than either of them could be on their own. So that's the overview of the periodic table and the explanation for the trends. Remember, anytime I ask you a question about trends, I need you to talk about 2 things: the effective nuclear charge, and you better talk to me about shielding. Those are the 2 important things, and you have to tell me about both for each of the atoms that you're discussing in your comparison. That's how you earn full credit on an AP question about nuclear trends. You discuss shielding and effective nuclear charge for both elements that you're asked to compare. That's it, guys. I'll see you soon.